Usually when we talk about a medical diagnosis or, I don't know, a structural engineering report, there is this fundamental expectation of precision.
Right.
Yes.
You expect a definitive answer.
Exactly. Like if you fall off a ladder and you break your arm, you go to the hospital, the x-ray shows that jagged glowing white line through the bone, and the doctor just points at the screen and says, well, there it is. That's the problem.
It is a binary state. The bone is broken or it is intact. We build our entire understanding of the world on that kind of macroscopic certainty.
Right. It is comforting. We like things to be visible. We want our reality to be categorized into neat little boxes. Solid, liquid, gas, safe, dangerous, existing, not existing.
But the universe at its most fundamental level does not oblige that desire for simplicity.
It really doesn't. Because you take a step past chemistry, past basic physics, and you wade into the world of quantum field theory. You start looking at the foundational architecture of the cosmos, and suddenly, that comforting X-ray machine is just totally shattered. We're looking at a diagnostic landscape of reality itself that is, honestly, incredibly murky.
And hidden in that murkiness is a mathematical mechanism that is profoundly unsettling.
Unsettling is putting it mildly. We're talking about a scenario where the universe literally has a self-destruct button, and the absolute worst part, we don't even know if it has already been pressed.
From a purely analytical standpoint, it is the absolute definition of existential dread. But I have to stress, it is not a fringe theory. It is rooted entirely in the hard mathematics of the standard model of particle physics.
So today, for you listening at home, we were going into the ultimate mindfuck. We are doing a deep dive into a concept called false vacuum decay. And I just need to warn you, whether you're commuting, sitting at your desk, walking your dog, I really need you to brace yourselves for this one.
It is an extreme concept.
Because this isn't about, like, a meteor hitting the Earth or the sun burning out billions of years from now. This is an event that would essentially erase the laws of physics themselves, just sweeping across the cosmos at the speed of light.
And to give you a comprehensive understanding of this, we aren't just looking at a single source. We are synthesizing a massive stack of modern physics literature.
Right. We've got theoretical reviews from Frontiers in Astronomy.
We're also looking at the foundational mathematics of Sidney Coleman from 1977.
Plus the 2024 experimental studies on supercooled atoms out of Newcastle University. And we're even digging into a recent survey of top physicists from the Effective Altruism Forum. The one where they debate the actual existential risk of alien civilizations triggering this by accident.
The scope is vast, because to understand the mechanics of this cosmic self-destruct mechanism, we first have to completely rebuild your understanding of what empty space actually is.
Yeah, we have to start from zero, literally.
Exactly. We need to look at why the mathematics governing our physical laws suggest this space is unstable, how a decay event would theoretically trigger at the subatomic level, and what the irreversible consequences would be for everything trapped inside the expanding bubble of a new reality.
We're drawing a line from the tiniest subatomic quantum fluctuation directly to the final fate of the entire accessible universe. And I have to be completely honest with you and with everyone listening. Just reading through the prep material for this deep dive gave me a literal pit in my stomach.
I can understand that reaction.
It's just the idea that me sitting here, you sitting across from me, the listener tuning in right now, the stars, the whole history of human existence, could just be deleted. Not burned, not smashed into pieces, but fundamentally rewritten out of existence in a fraction of a microsecond. And without any warning whatsoever, it is viscerally terrifying.
The human brain is simply not evolved to process the instantaneous cessation of existence. But if we can step back from the emotional weight for a moment, from a purely analytical perspective, it is a fascinating, almost staggeringly beautiful consequence of the physical laws as we currently understand them.
Beautiful. I don't know if I'd use the word beautiful.
It is mathematically elegant. This isn't science fiction. It is a mathematical inevitability born from the exact parameters we have measured in particle accelerators. It is a rigorously studied feature of the Higgs field.
Okay, so let's jump right into that. Because to understand how the universe can just delete itself, we have to start by fundamentally breaking down what nothingness actually is.
That is the correct starting point.
Because I think when I or anyone listening thinks of a vacuum, we picture empty space. Like, imagine you take a reinforced steel box, you pump out all the air, you use lasers to remove every single stray atom, you shield it from all background radiation, heat, light, everything. You look inside that box and you have nothing. Just an empty void.
Right. That is the classical Newtonian intuition, yes. It makes perfect sense to our everyday experience. But quantum field theory tells us a radically different story.
So the box isn't empty.
True emptiness, in the way you just described it, does not actually exist. Space is not a void, it is a medium. It is permeated by quantum fields that exist at every single coordinate, every single point in the entire universe.
What exactly is a quantum field, though, for people who aren't quantum physicists?
Think of a field as an invisible, universe-spanning fluid. There is an electromagnetic field, an electron field, an up-quark field, and so on. What we perceive as a physical particle like a photon of light or an electron orbiting an atom is not an isolated little billiard ball.
Okay.
It is simply a localized ripple, a localized excitation in its corresponding underlying field. If you pluck the electron field with enough energy, an electron pops out.
So the universe is basically a giant ocean made of dozens of different overlapping fluids, and particles are just the waves on the surface.
Precisely.
Okay.
Now, return to your sealed, perfectly shielded steel box. You have removed all the particles, you have calmed all the waves, but the oceans are still there.
Wow.
The fields haven't gone anywhere. The vacuum is simply the state where all of these quantum fields are as quiet, as still, and as low energy as they can possibly be. It is the absolute ground state.
So a vacuum is just the universe on mute.
That is a brilliant way to put it, yes. And for almost every single field in the standard model, like the electromagnetic field, that muted lowest energy state corresponds to a mathematical value of exactly 0.
Meaning what, practically?
When the electromagnetic field is resting at 0, there are no ripples, there are no photons, there is no light. It is empty in that specific regard.
But there's a rebel in the group.
Right.
One field that refuses to go to 0.
Yes. The Higgs field. The Higgs field is entirely unique within the architecture of the standard model because its lowest energy state, its resting equilibrium, the quietest it can possibly be, does not have a value of 0.
Right.
It has a real, positive, non-zero value everywhere in the universe.
This is where my brain starts to skip a beat. You're saying that empty space is actually completely full of this background Higgs energy. Like, even when it's doing absolutely nothing, it has a physical presence.
It is a ubiquitous, invisible soup. It permeates your body, the room we are sitting in, and the deepest voids of intergalactic space equally. And this non-zero resting value isn't just a quirky mathematical footnote, it is absolutely critical for our existence.
How so?
The Higgs field is the mechanism that gives elementary particles their mass.
Okay, I need to stop you there, because giving particles mass is one of those phrases that gets thrown around in high school physics, but it's incredibly hard to visualize. How does an invisible soup give things mass?
Let's look at the carriers of the weak nuclear force, the W and Z bosons, or the quarks that make up the protons and neutrons in your body.
Okay.
In a universe without the Higgs field, or if the Higgs field rested at a true 0 value, the mathematics dictate that all of these fundamental particles would be entirely massless.
Like photons. Like light.
Exactly. And particles without mass must, by the laws of relativity, travel at the speed of light. They cannot slow down. They cannot group together.
Wait, so if the Higgs field were at 0?
The quarks in your body would suddenly lose their mass and zip away at light speed. The protons would instantly disintegrate. Atoms wouldn't just fly apart. They could never have formed in the first place.
So what does the Higgs field actually do to stop them, like mechanically?
Because the Higgs field is resting at a positive non-zero value, it acts like a kind of cosmic molasses. As these fundamental particles try to move through space, they constantly interact with and bump into this background Higgs field.
Right, they get bogged down.
Yes, that constant interaction, that drag, is what manifests as the property we measure as mass. It slows them down, it allows them to bind together. It breaks the underlying symmetry of the universe, allowing complex, structured matter-like stars, planets, and biology to exist.
Okay, I was reading through the sources, specifically the PBS Spacetime one, and I had this massive aha moment with an analogy they used. I think it perfectly visualizes why this is so weird.
Go ahead.
Imagine space isn't just empty air, but it's made of millions of tiny invisible rubber rings at every single point. If you compress one of those rings, you're putting energy into it. You're exciting the field. But the ring wants to snap back to its uncompressed state. It wants to shrink down to nothing, to 0 energy. That represents all the normal fields, like the electron field.
Yes, that is a highly effective way to visualize a standard harmonic oscillator in quantum mechanics. The resting state is 0.
But the Higgs field is different. The Higgs field is like a rubber ring that has been stretched and wrapped around a physical solid pole. Its relaxed state, its minimum energy state, isn't shrunken down to a pinpoint of nothingness. It's resting tightly around the width of that pole.
Because the pole prevents it from shrinking any further.
Exactly. It is physically impossible for it to shrink to zero because the pole is in the way. It wants to be stretched out a little bit.
That is a phenomenal conceptualization. The width of the pole perfectly represents what we call the non-zero vacuum expectation value of the Higgs field. It rests at roughly 246 billion electron volts. That is the baseline of our reality.
So if we bring this all together, what you're saying is that empty space, like the space between my hands right now, the space inside the listener's living room, is actually a dense, heavy ocean of Higgs energy. And our entire physical reality, every chemical reaction, every biological cell, relies entirely on the water level of this ocean staying exactly where it is.
Yes.
And if the water level changes, we die.
Die is entirely the wrong word.
How is it the wrong word?
Because death implies a biological end within a continuous physical framework. If the Higgs field's vacuum expectation value were to change, the physical framework itself collapses. We would cease to be possible. The structural integrity of reality, the very constants of nature, rely entirely on that exact water level remaining stable.
Oh, man. And that realization is the perfect pivot to the deeply uncomfortable question at the heart of all this deep dive. Because now that we know space is filled with the Higgs field resting at this specific non-zero value, we have to ask, is it actually resting at the absolute bottom of the energy landscape? Right. Or is it just stuck on a ledge?
This is the crux of the metastability problem. In physics, and specifically in the mathematics of potential energy, we must differentiate between a local minimum and a global minimum.
Break that down for me. What's the difference?
Imagine a vast, sprawling landscape of rolling hills, deep ravines, and valleys. A global minimum is the absolute lowest possible point in that entire landscape. Yeah. It is the Mariana Trench of this theoretical energy map.
Okay, I picture that.
If you drop a boulder and it rolls all the way down into that global minimum, it is absolutely permanently stable. It can never, ever roll down any further because there is literally nowhere lower for it to go. This state of absolute lowest energy corresponds to what we call a true vacuum.
Right. Gravity, or in this case, the universe's tendency to seek the lowest energy state, has done all its work. The boulder is safe.
Exactly. But a local minimum is different. Imagine the boulder is rolling down a massive mountain, but halfway down it falls into a small crater or a depression on the side of the slope.
So it stops rolling.
Yes. The boulder sits in that crater. It doesn't move. To the boulder, and to anyone standing in that crater, it seems perfectly stable. It feels like the bottom of the world.
Because you can't see over the edge of the crater.
Precisely. But if you were to look at the larger macroscopic landscape, you would see that there is a massive, infinitely deeper valley much further down the mountain. The boulder is merely trapped by a small ridge of dirt. This crater is a false vacuum. It is metastable. It is stable for a long time, but not forever.
This reminds me of an incredible analogy I read in one of the highly technical Reddit AMAs we sourced. They explained it like a marble rolling into a bowl. But the bowl isn't a perfect sphere. It has an inner lip, like a tiny gutter running along the inside halfway down the slope.
A local minimum.
Right. You drop the marble in, it rolls around, and it gets wedged in that gutter. And the thing is, our entire universe, the galaxies, the listener, the laws of physics, we are that marble. We look around, everything is completely stable, everything is unchanging. We think we're sitting firmly on the floor.
But we are not.
No, there is a trapdoor right beneath us and an unfathomably deeper floor below.
The geometry of the gutter perfectly captures the mathematical shape of the Higgs potential. And the deeply unsettling part is that we aren't just guessing about the existence of this deeper floor.
We have proof.
The reason we suspect we are trapped in that gutter comes down to two very specific, incredibly precise measurements made at the Large Hadron Collider in Switzerland.
And what are those?
The mass of the Higgs boson and the mass of the top quark.
Okay, I want to really dig into this because on the surface it sounds absolutely absurd. You're telling me that humanity built a massive underground ring, smashed some protons together, measured the mass of two incredibly tiny subatomic particles, and from those two solitary numbers, we can calculate the ultimate fate of the entire cosmos. Like, how does that even work?
It works because in quantum field theory, particles do not exist in isolation. They constantly interact or couple with one another, and the strength of those interactions dictates the overarching shape of the universe.
Okay.
Now, let's look at the numbers. The Higgs boson has been measured to have a mass of approximately 125.66 gigaelectron volts, or GeV.
which is pretty heavy for a subatomic particle.
It is, but the top quark is even heavier. In fact, the top quark is the heaviest elementary particle we have ever discovered, weighing in at roughly 173 GeV.
Wow, okay.
Now, here's where the physics gets incredibly unintuitive. In quantum field theory, the numbers that dictate how strongly fields interact with each other are called coupling constants, but they're not actually constant.
Wait, how can a constant not be constant?
Because they change their value depending on the energy scale at which you are observing them.
Oh, right. Because of quantum fluctuations. The idea that empty space is boiling with virtual particles popping in and out of existence.
Precisely. If you place a bare electric charge in a vacuum, a cloud of virtual electron-positron pairs will swarm around it. The virtual positrons are attracted to the negative charge, and the virtual electrons are repelled.
Makes sense. Opposites attract.
This cloud of virtual particles acts as a screen. It physically shields the bare charge. So if you measure the charge from far away, at a low energy scale, it looks weak.
Because it's being blocked by the cloud.
Yes. But if you probe it with a high-energy particle that penetrates that virtual cloud and gets closer to the core, the effective charge you measure gets stronger. The constant has changed based on your energy scale.
That is incredibly weird, but it makes sense.
Yeah.
So how does this apply to the Higgs field in the top quark?
The shape of the Higgs energy landscape, the shape of the bowl the marble is sitting in, is determined by a specific parameter called the Higgs-Quark coupling. It is denoted by the Greek letter lambda.
Lambda. Got it.
For our universe to be absolutely stable, for us to be resting at the absolute bottom of a true vacuum, the value of lambda must remain positive across every conceivable energy scale, all the way up to the Planck scale.
Meaning the bowl just keeps going up.
If lambda is positive, the walls of the bowl curve upwards infinitely. You are safe.
But I'm guessing lambda doesn't say positive.
It doesn't appear to. This is where the top quark ruins everything. Because the top quark is so incredibly massive, its interaction, its coupling with the Higgs field is immensely strong.
Right.
We use complex mathematical formulas called renormalization group equations to calculate how lambda changes as you scale up to higher and higher energies. In these equations, the interaction of the heavy top quark provides a powerful negative contribution to the value of lambda.
So as we look closer, as we scale up the energy, the heavy top quark is basically dragging the value of lambda down.
Exactly. Think of the top quark as an incredibly heavy weight hanging off the side of the bowl. As you scale up to enormously high energies, around 10 to the 10th power GeV, which is billions of times more energetic than anything we can produce in the Large Hadron Collider, the negative influence of the top quark overwhelms the equations.
And what happens to lambda?
The value of lambda is dragged so far down that it actually crosses zero. It flips from a positive number to a negative number.
And if lambda is negative, what does that mean for the shape of the bowl? What happens to the marble?
If lambda becomes negative, it means the bowl turns upside down.
Oh, God.
The potential energy landscape stops curving upwards to protect us, and instead it crests a ridge and slopes steeply, infinitely downward. Mathematically, a negative lambda at high energies guarantees that a second, significantly deeper minimum exists further out in the field space.
Meaning a true vacuum exists.
Yes. The sheer existence of that deeper valley mathematically proves that our current resting place is merely a local minimum. We are in the false vacuum.
I am trying to visualize this. We are sitting in a tiny divot on the side of a sheer cliff face. And we only know the cliff goes down forever because we weighed a top quark and did the math.
That is an accurate summation.
But here's where it gets agonizing. The sources, specifically those theoretical physics reviews, mention that we aren't exactly 100% sure we are right on the razor's edge of the math.
That is correct, and it is a source of intense debate in the physics community. If you draw a stability diagram, a graph plotting the mass of the top quark on one axis against the mass of the Higgs boson on the other, you find that our universe sits directly in the metastable region.
Barely, right?
Yes, we sit agonizingly close to the boundary line of absolute stability. The uncertainties in our measurements, particularly the exact mass of the top quark, are just large enough that absolute stability hasn't been definitively entirely ruled out.
Wait, really? So there's a chance the math is just slightly fuzzy and we are actually safe in a true vacuum?
There is a statistically small chance, yes. The theoretical papers note that if we could reduce the uncertainties of the top quark mass and the strong force coupling constant by a factor of 2 to 3, we could definitively prove whether we are stable or metastable at a 5 sigma level of confidence.
5 sigma. That's the gold standard in particle physics, right?
Right.
That means there's less than a 1 in 3.5 million chance the result is a fluke. So how do we get that level of certainty? Do we just need to keep running the Large Hadron Collider for another decade?
The LHC will continue to refine the numbers, but reaching the 5 sigma threshold of precision likely requires a completely new next-generation facility. Physicists are proposing machines like the Future Circular Collider and Electron-Positron Collider spanning a 100-kilometer ring.
That's massive.
It would be capable of performing incredibly clean, interference-free threshold scans of top quark pair production. But until that machine is built, which could be decades away, the current central values of the math point squarely, unmistakably, to a metastable false vacuum.
So we basically have to assume the worst.
As rational observers, we must operate under the assumption that the trapdoor exists.
Okay, so we assume the trapdoor is real. The marble is stuck in the gutter. The universe is metastable. If we accept that deeply unsettling premise, we have to look at what happens next. If we are balancing precariously on a ledge, what does it take to actually push us off? Because honestly, if it takes an infinite amount of energy to push the marble out of the gutter, who cares?
Okay.
Right? We're safe.
If the universe were purely classical, if it obeyed only the predictable macroscopic laws of Newtonian physics, you would be perfectly safe. In a classical system, to get a marble out of a deep gutter and over a ridge into a lower valley, you must physically push it.
Right, you need energy.
You have to implement a massive amount of kinetic energy to overcome the potential energy barrier of the ridge. If no external force interacts with the marble, it sits there for eternity.
But we don't live in a classical universe. We live in a quantum universe.
We do. And in a quantum universe, the fundamental rules of reality are governed by probability and the Heisenberg uncertainty principle. In the quantum realm, the marble does not actually need to climb over the hill. It can simply tunnel through it.
Quantum tunneling, the ultimate cheat code of physics. I've always struggled to understand this. How does something just go through a solid barrier without the energy to break it?
Think of a quantum particle not as a solid marble, but as a smeared-out cloud of probability. This cloud, the wave function, describes the likelihood of finding the particle at any given location.
Okay, I'm with you.
When this probability wave hits a solid barrier, it doesn't just stop instantly. The wave decays exponentially inside the barrier. But if the barrier is thin enough or the physics align, a tiny, faint fraction of that probability wave bleeds through to the other side.
So there's a tiny, non-zero mathematical chance that the particle just exists on the other side of the wall.
Precisely. You don't see this in microscopic life. If you throw a tennis ball against a brick wall 1 trillion times, it will bounce back 1 trillion times. But if you throw an electron at a nanoscale barrier, occasionally, the electron simply vanishes from one side and instantly reappears on the other, without ever passing through the space in between.
And this applies to the vacuum of the universe.
Yes. The entire Higgs field can undergo quantum tunneling. It's a field configuration passing through a classically forbidden energy barrier. It's as if the entire ocean of the Higgs field, at some microscopic point, simply vanishes from the false vacuum gutter and instantly reappears on the downward slope of the true vacuum.
Just like that.
No external energy required, no alien laser beam, no exploding star. The universe doesn't even need a push.
This is the mind-bending horror of it. I want to make sure you, the listener, are really grasping this. You were telling me that reality does not have to climb over the wall. The universe can just magically, probabilistically phase through the wall at any random second with absolutely zero warning and zero external force.
Yes. The mathematical framework for this nightmare was famously established in 1977 by the theoretical physicist Sidney Coleman. He published a seminal paper describing the exact process of false vacuum decay. He called it bubble nucleation.
Bubble nucleation.
It is essentially a direct extension of ordinary quantum tunneling, but applied to the entire fabric of field theories.
One of the sources, the PBS Spacetime Deep Dive, compares this to a pot of boiling water. And I thought this was brilliant. When water boils, it undergoes a phase transition from liquid to gas. But the entire pot doesn't turn into steam all at once. The transition starts with microscopic, tiny bubbles of steam forming randomly inside the liquid.
Bubble nucleation. It is a nearly perfect analog. In the quantum vacuum, fluctuations are constantly, ceaselessly happening. Empty space is boiling with energy. Most of the time, these quantum fluctuations are tiny. The Higgs field might temporarily sample a lower energy state in a microscopic region, creating an incredibly tiny subatomic bubble of the true vacuum.
But obviously, those tiny bubbles don't destroy the universe. Why not?
Yeah.
Why doesn't the first tiny bubble just consume everything?
Because of the physics of surface tension. Just like a bubble of steam in water, a bubble of true vacuum has a physical boundary. It has a domain wall that separates the chaotic true vacuum on the inside from the stable false vacuum on the outside.
Okay.
Creating that wall requires a massive amount of energy. Now, the interior volume of the bubble releases energy because it is dropping to a lower, more stable energy state. But the surface area of the wall costs energy to maintain.
So it's a fundamental tug-of-war. The inside wants to grow, the outside wants to crush it.
Exactly. And we have to look at the geometry. The volume of a sphere scales as the cube of the radius, while the surface area only scales as the square of the radius. This means for very small bubbles, the surface area mathematically dominates the volume.
Which means
The energy cost of the wall is far greater than the energy saved by the interior. So these microscopic bubbles are crushed out of existence almost instantly. They are dominated by surface tension. They simply cost too much energy to sustain.
But if a quantum fluctuation manages to randomly form a bubble that is just large enough,
Then it crosses a terrifying mathematical threshold known as the critical radius. It's denoted as R sub c. At that exact, highly specific size, the energy gained from the volume perfectly exactly balances the energy cost of the surface wall.
a moment of perfect equilibrium.
Yes, and the instant the bubble fluctuates to be even a fraction of a nanometer larger than R sub c, the math flips. The volume drastically dominates the surface area. The bubble becomes energetically favorable.
And once it becomes energetically favorable, it begins to expand.
Indefinitely. It is an unstoppable runaway reaction. The bubble will relentlessly expand outward and consume the entire accessible universe.
Okay, so the obvious question is, how likely is it that a bubble exactly that big just randomly blips into existence? What are the odds we roll that specific quantum die?
Sidney Coleman calculated this probability using a brilliant, albeit intensely complex mathematical trick called the bounce solution. To solve the tunneling equations, he rotated the mathematics into Euclidean space.
I'm going to need you to Eli 5 Euclidean space and bounce solutions, because that sounds like pure magic.
It is a mathematical sleight of hand. Calculating tunneling in normal space and normal time is incredibly difficult. But physicists realize that if you multiply the time coordinate by the imaginary number, I, the square root of -1 time, mathematically transforms into a fourth spatial dimension.
Wait, what?
You move from our normal Lorentzian space-time into Euclidean space, where time behaves exactly like length, width, and height.
Wait, you literally turn time into a direction.
Mathematically, yes. It turns a dynamic, moving, impossible-to-calculate tunneling event into a static, perfectly symmetrical, four-dimensional geometric shape. Coleman calculated what is called the Euclidean action, S sub e, of this four-dimensional shape.
And what does that tell us?
Without getting bogged down in the derivations, the key takeaway is that the Euclidean action tells you the exact probability of the decay happening.
And what is the number? How long do we have before the universe rolls a 1?
The math reveals that the tunneling rate is exponentially suppressed. The Euclidean action is incredibly, staggeringly large. This means the probability of a critical bubble forming in any given volume of space per unit time is infinitesimally small. The calculated lifetime of our false vacuum, based on the current mass of the top quark, is somewhere in the range of 10 to the 65th power to 10 to the 794th power years.
Let me just pause and let that number sink in. 10 to the power of 794 years. That is a 1 with 794 zeros after it. That is an absurdly, unfathomably long time. Just to give the listener context, the entire universe is only 13.8 billion years old. That's roughly 10 to the power of 10.
Yes.
So we are talking about a lifespan that makes the current age of the universe look like a millisecond. It's practically eternity.
Statistically speaking, yes. A direct calculation within the standard model finds that the lifetime of the false vacuum is greater than 10 to the 65th power years with a 95% statistical confidence level. If the universe were infinitely old, the decay would be an absolute mathematical certainty. But given our universe's relatively young age, spontaneous quantum decay is highly, highly unlikely to happen tomorrow.
But here's the thing that absolutely haunts me. Highly unlikely is not impossible. That's the insidious nature of quantum mechanics. It is a probability curve. It's like rolling a trillion-sided die every single second. Yes, the odds of rolling a 1 are vanishingly small, but the die has no memory. You could roll a 1 tomorrow.
That is the uncompromising nature of a probabilistic quantum event. It could happen tomorrow, it could happen 10 seconds from now. Or, vastly more likely, it could have already happened a billion years ago in some distant, unmapped galaxy.
Which leads us perfectly to the next horrifying phase of this deep dive. Let's say it happens. Somewhere out there in the cosmos, perhaps millions of years ago, a bubble of true vacuum nucleates. It hits the critical radius, the math flips, and it starts to grow. What does that growth actually look like?
Once the bubble exceeds the critical radius, the microscopic quantum dynamics are replaced by the macroscopic laws of relativity. The energy difference between the metastable false vacuum outside and the ultra-low energy true vacuum inside is vast. As the bubble expands, it is physically converting false vacuum into true vacuum.
And all that stored energy has to go somewhere, right?
Yeah.
Conservation of energy.
Exactly. And it goes directly into accelerating the bubble wall. The domain wall is constantly being pushed outward by the enormous crushing pressure difference of the lower energy state inside. Because of this continuous massive injection of energy, the wall's velocity asymptotically approaches the speed of light almost instantaneously.
So it's essentially an invisible sphere of utter annihilation expanding in all directions at light speed.
Yes. Now, there is a fascinating, highly technical nuance here discussed in the physics papers we reviewed, specifically looking at the concept of cosmological friction.
Friction in space.
Remember, the universe is not a perfect, empty void. The bubble wall isn't propagating through absolute nothingness. It is propagating through our universe, which is filled with a thin plasma of gas, background radiation, entire galaxies, and dark matter.
And hitting all that stuff causes friction against the bubble wall.
Correct. The domain wall forces the particles it encounters to undergo violent phase transitions. It is essentially sweeping them up or annihilating them. This continuous interaction acts as a physical damping force. Several physicists have calculated that this immense friction could theoretically prevent the wall from exactly reaching the speed of light. It might reach a terminal velocity that is just a fraction of a hair below the universal speed limit.
Okay, so what does that mean in practical terms for us? If the bubble is expanding just a tiny microscopic bit slower than light, could we see it coming? Could we get a warning?
In pure theory, yes. One of the papers calculated a hypothetical scenario. If a bubble were created 1 million light years away, and the friction of the cosmic plasma slowed the wall by just 1 kilometer per second relative to the speed of light, the light emitted by the violent particle interactions at the wall could reach Earth about 3 years before the physical wall itself.
3 years. We would have a 3-year warning.
You would look up into the night sky and see an incredibly intense, utterly bizarre flux of high-energy particles and anomalous radiation expanding outward, heralding the edge of the true vacuum.
Imagine the absolute chaos of that. 3 years of human civilization just sitting around looking at a glowing, expanding ring in the sky, completely powerless, waiting for the delete button to hit us. But the sources also say that, practically speaking, this is a light speed event, right?
Yes. The terminal velocity is so extraordinarily, imperceptibly close to the speed of light that for all intents and purposes, it is a light speed event. And if it travels at exactly the speed of light, or close enough to it, we are fundamentally perfectly blind to it.
I want to break this down for the listener, because this is the part that breaks my brain. Why are we blind?
Because of the causal structure of space-time. Information cannot travel faster than light. If the bubble wall is approaching you at the speed of light, the photons, the light rays bouncing off the wall, are traveling at the exact same speed as the wall itself. The information of your destruction arrives at your eye at the precise, exact instant the physical wall hits your body.
So let's make this uncomfortably real. Think about what you're doing right now. You are listening to our voices, you are breathing, you are experiencing the flow of time. A completely invisible bubble of true vacuum could have swallowed the sun 8 minutes ago. It could be sweeping through the vacuum of the solar system right now, crossing the orbit of the moon. You wouldn't see the sky go dark, you wouldn't feel a sudden chill, the gravity of the Earth wouldn't shift. You are totally, fundamentally blind to your own cosmic executioner. The exact moment your brain is capable of perceiving the visual light of the bubble, your brain no longer exists to process it.
It is a profound, chilling realization of our causal limits. We exist inside what physicists call a light cone. We can only be affected by things that have had time to reach us at the speed of light. Anything approaching along the absolute edge of that cone is invisible until the very moment it intersects our reality.
Okay, so let's talk about the intersection. The wall hits the Earth. It passes through my body, your body, the listener's body. What exactly goes down inside the bubble? I know it's bad, but I want to understand the hard physics of why it's bad.
Sidney Coleman, in his profoundly bleak, poetic style, described it as the ultimate ecological catastrophe. When the bubble wall passes through a region of space, the Higgs field instantly drops from its current false vacuum value to its new true vacuum expectation value. In an instant, the foundational constants of nature are completely rewritten.
It's like a computer hard drive getting completely reformatted while the operating system is still running.
That is a very accurate analogy. Remember earlier when we discussed how the background interaction with the Higgs field gives elementary particles their mass?
Yeah, the cosmic molasses.
Exactly. In the new true vacuum, the resting value of the Higgs field is vastly different. The mathematics suggest it would likely be orders of magnitude higher. Instantly, in the span of a Planck time, the masses of the elementary particles making up your body, the electrons orbiting your atoms, the quarks inside your protons, would change drastically. They might become massively, impossibly heavier.
And what does that do to a physical atom, like a carbon atom in my DNA?
It destroys it utterly. The structural integrity of an atom relies on an incredibly delicate, fine-tuned balance between the electromagnetic force holding the electrons in their orbital shells and the physical mass of the electrons themselves. If an electron suddenly weighs 10,000 times more, its quantum orbit shrinks catastrophically. The electrons would collapse into the nucleus, protons themselves might destabilize and decay instantly. The weak nuclear force would operate over an entirely different range.
So chemistry just stops.
Chemistry is impossible. Biology is impossible. The complex, beautiful molecular bonds that form DNA, proteins, water, the air we breathe, they all require the precise, arbitrary tuning of our current false vacuum. In the true vacuum, matter as we know it cannot exist in any form. Every complex structure would instantly, violently disintegrate into a chaotic, unrecognizable soup of unfamiliar, ultra-heavy particles.
It's not just that we die. That's the part that is so hard to convey. A supernova kills you. A black hole kills you. This is something else entirely. It's that the rules of existence, the very physical laws that allowed consciousness to arise, are rewritten so that we could never have existed in the first place. Reality hits factory reset and bricks the universe.
And the physics dictate that it gets even more extreme than the disintegration of atoms. It is not just matter that is destroyed, it is the very fabric of space-time itself.
Wait, hold on. Space-time is destroyed. How does a changing field destroy space?
This goes back to a highly influential 1980 paper by Sidney Coleman and his colleague Frank DeLucia. They took the basic idea of vacuum decay and incorporated the effects of general relativity and gravity. We have to look at the energy density of the vacuum. The false vacuum we currently inhabit has a tiny but positive intrinsic energy density.
Is that what we call dark energy, the stuff making the universe expand faster?
Exactly. That positive vacuum energy acts as a repulsive gravitational force stretching the universe apart. We live in a geometry that physicists call roughly de Sitter space. It is expanding and relatively flat.
Okay, so the false vacuum has a tiny positive energy. What about the true vacuum inside the bubble?
By its very mathematical definition, the true vacuum is a much, much lower energy state. In almost all theoretical models of this transition, the energy drop is so massive that the energy density of the true vacuum becomes highly negative. And according to Einstein's equations of general relativity, a negative vacuum energy density fundamentally alters the geometry of spacetime, creating what is known as anti-de Sitter, or ADS space.
Anti-de Sitter space. I've heard the term in string theory, but what does it actually mean for anyone trapped inside the bubble?
It means your doom is compounded. Anti-de Sitter space with a highly negative cosmological constant is violently, aggressively unstable. In our universe, positive dark energy pushes space apart. In AdS space, the negative energy creates a massive, overarching attractive force. The curvature of space itself causes everything to violently contract. Within microseconds of the bubble wall passing through and establishing the true vacuum, the interior space undergoes a localized, catastrophic gravitational collapse.
A big crunch.
Yes, a localized big crunch. The space inside the bubble instantly collapses in on itself, crushing down into an infinitely dense mathematical singularity. So you don't just have your atoms disintegrate into a heavy quark soup. The actual spatial dimensions you exist in length, width, height, and time fold up and crush themselves completely out of existence in a fraction of a millisecond.
I don't even know how the human brain is supposed to process that. It's an erasure so total, so absolute, that it literally deletes the canvas the universe was drawn on. You don't leave a corpse. You don't leave ruins. You leave literally nothing.
It is the absolute definitive end of our localized reality. It is a boundary past which no physical laws we understand can be applied.
So naturally, knowing that this sort of Damocles is hanging over our heads, I want to know if there's anything out there that can speed this up. We established earlier that spontaneous, purely random quantum tunneling takes 10 to the 794th power years. Statistically, we have time. But is there a catalyst? Is there a spark that could set this off prematurely, either out in the cosmos or right here on Earth?
This exact question is a highly active, fiercely debated area of research in modern physics. Physicists are actively looking for environments in the universe with extreme localized energy densities or severe gravitational curvatures that might artificially lower the potential barrier, making tunneling drastically easier. We have to examine both naturally occurring cosmic phenomena and the potential of our own, or an alien civilization's technology.
Let's start with the cosmos. Because the universe is incredibly violent.
Oh.
Did the early universe almost kill us before we even started?
It very nearly might have. The most dangerous, perilous time for the survival of the false vacuum was during an epoch known as cosmic inflation, occurring just fractions of a second after the Big Bang. During inflation, the universe expanded at a literally incomprehensible exponential rate. And during this violent expansion, the Higgs field was subjected to massive, chaotic quantum fluctuations.
If we go back to the marble analogy, inflation is like a giant hand violently shaking the bowl the marble is resting in.
That is exactly what happened. The rapid expansion of space acts almost like a boiling thermal bath, injecting massive amounts of ambient energy directly into the Higgs field. The very fact that our universe survived inflation, that the marble didn't just instantly bounce out of the gutter and doom the universe before stars could even form, places extremely tight bounds on our understanding of physics.
Like what kind of bounds?
Specifically, it constrains a parameter called Xig, which dictates the non-minimal coupling of the Higgs field to the curvature of spacetime. If Xa isn't tuned to a very specific, narrow range, the intense gravitational curvature of the early universe would have driven the Higgs field over the edge instantly.
But we survived. The marble stayed in the gutter. So Xe must be safely fine-tuned. What about something happening today? What about black holes? They have the most intense gravity in the modern universe.
Black holes are indeed prime suspects, but not just any black hole. Physicists specifically look at microscopic primordial black holes. These are hypothetical, ultra-dense black holes left over from the dense, crushing forces of the early universe. They might only be the mass of a mountain, but shrunk down to the size of a proton. The extreme, intensely localized gravity near their microscopic event horizons could act as a nucleation seed.
How does gravity act as a seed? Does it pull on the field?
It severely distorts spacetime in a way that effectively, mathematically lowers the potential barrier for the Higgs field to tunnel through. Think of it as a flaw in a pane of glass. It is much easier for the glass to shatter starting at the flaw. Furthermore, these tiny black holes emit Hawking radiation. They are incredibly hot. This heat injects thermal energy into the field around them. Between the gravitational distortion and the thermal heat, a true vacuum bubble could form around a primordial black hole vastly more easily than in empty space.
Okay, so a tiny, invisible black hole floating out in the void between galaxies could be the cosmic detonator. What about cosmic rays? These are the highest energy particles in the universe, fired out of supermassive black holes, slamming into each other at nearly the speed of light. Could a collision like that spark a bubble?
That was a major, highly publicized concern for a while. If two ultra-high-energy cosmic rays collide head-on, could they concentrate enough pure kinetic energy in one microscopic spot to just kick the field completely over the barrier? An extensive, highly detailed theoretical paper by physicist Alessandro Strumia analyzed this exact terrifying scenario. And the answer, fortunately for us, is reassuringly no.
Why not? If they have enough raw kinetic energy to climb the hill, why doesn't the marble just fly out of the bowl?
Because of the complex nature of the quantum phase transition, to trigger vacuum decay, it's not enough to just dump a massive chaotic amount of thermal or kinetic energy into a single point. You aren't just heating up a rock. You need to create a coherent, specific field configuration that perfectly resembles the critical bubble we talked about earlier. In the language of quantum mechanics, this requires producing roughly n overlapping Higgs bosons, where n is dictated by the equation 4 pi divided by the quartic coupling lambda.
Let me guess, that's not a small number.
It translates to roughly 1,000 Higgs bosons.
Wait, so to trigger the decay, you need to smash two particles together, and instead of just exploding into random debris, they have to produce exactly 1,000 Higgs bosons, all perfectly overlapping in the exact same quantum state. in a microscopic volume.
Correct. You need a highly organized, flawlessly coherent macroscopic state of bosons. The probability of two colliding elementary particles randomly producing a perfectly organized spherical cluster of 1,000 bosons is exponentially suppressed. The math shows it has what we call an X negative O of n suppression.
Can you translate that into human odds?
Imagine dropping 1,000 coins from an airplane and requiring every single one of them to land perfectly on their edge, standing straight up, perfectly aligned in a circle. The sheer raw energy of the collision doesn't matter if the energy disperses chaotically. Sturmia's mathematical proof refers to this as no Higgs explosion. The likelihood of a high-energy collision accidentally organizing itself into a critical bubble is just as astronomically unlikely as spontaneous quantum tunneling.
So it's not just about raw power. It's about perfectly arranging the energy. Okay, so cosmic rays are safe, but what if you did want to organize it perfectly? What about advanced technology? In our stack of sources, there's a totally fascinating survey from the Effective Altruism Forum. They surveyed 20 of the world's leading physicists, specifically about existential risk and vacuum decay. What did they find out?
The survey results are highly illuminating regarding expert consensus, or more accurately, the severe lack thereof. When these top physicists were asked if they believe the vacuum is actually metastable, the average response was a 45.6% probability.
Wait, almost 50-50. So it's essentially a coin toss among the smartest people on Earth, whether the standard model holds true and the trapdoor actually exists.
Yes. It highlights just how deep the uncertainties in our current measurements are. But then the survey asked a much more provocative, unsettling question. Assuming the universe is metastable, what is the probability that arbitrarily advanced technology could deliberately or accidentally induce vacuum decay? The average response from the physicists was 18.8%.
Nearly a 1 in 5 chance. That is terrifyingly high.
You have to look at the distribution of the data. That 18.8% average is heavily skewed by a few respondents who believe it is highly likely. However, 55% of the physicists surveyed stated definitively that there is a solid 0% chance that even arbitrarily advanced technology could ever induce decay.
I don't understand how they can say 0%. If an alien civilization is arbitrarily advanced, shouldn't they be able to manipulate physics to do anything?
The argument for 0% is twofold. First, there is the anthropic argument. The universe is incredibly old and unfathomably vast. If it were physically possible to engineer a vacuum decay event, some incredibly advanced galaxy-spanning civilization in the 13.8 billion year history of the cosmos likely would have done it by now, either by accident or on purpose. Since the universe is still here, and we are still here, it implies it must be physically impossible.
The ultimate survivor bias. We only exist because the universe is idiot-proof.
Exactly. The second argument is purely physical. Inducing the decay artificially requires manipulating quantum fields at energy scales approaching the Planck scale in a highly coherent manner. Many physicists believe the fundamental laws of quantum field theory strictly prohibit scaling up such an organized multi-particle transition, no matter how much energy or technology you command. It's like trying to build a perpetual motion machine. It's not a matter of better engineering, it's physically forbidden.
But 45% of them didn't say 0. And I can't stop thinking about the Kardashev scale. Imagine a Type 3 civilization that can harness the power output of an entire galaxy. What if they are testing a new warp drive or manipulating massive black holes to build a wormhole network, and they accidentally hit that exact resonant frequency? What if they accidentally spawn 1,000 coherent Higgs bosons in a perfectly spherical cluster? Or even worse, what if they use it as a weapon? A cosmic doomsday device that sweeps across the enemy's galaxy at the speed of light.
The Sturmia paper actually speculates on this exact dark scenario. He suggests mathematically that while two particle collisions absolutely cannot do it, an incoming, highly orchestrated, macroscopic wave of n-boosted Higgs bosons at a futuristic, galaxy-sized collider might theoretically induce the decay classically. But he also notes that as an energy source, or even as a weapon, it's deeply, fundamentally impractical.
Impractical how? If you want to wipe out your enemy, deleting the universe seems pretty effective.
Because you cannot control the bubble, you cannot direct it, and you cannot stop it. The moment you press the button, the moment you create the true vacuum, it expands outward at the speed of light in all directions. It destroys the enemy, but it inevitably, unstoppably destroys you, your homeworld, and everything you have ever built.
It's a suicide vest for the entire universe. That is the darkest Fermi paradox solution I've ever heard in my life. Where are all the aliens? Oh, the first one to build a galactic supercollider accidentally deleted the local supercluster.
It is a profoundly sobering thought experiment. But again, the physics required to overcome the exponential suppression factors and actually engineer that coherent state are monumentally, perhaps impossibly prohibitive.
Okay, so maybe the aliens can't do it, but we actually simulated this entire apocalypse in a laboratory. I want to move to the 2024 experimental study, because up until now, this has all just been chalkboard math and supercomputer models. But in 2024, scientists literally watched a false vacuum decay.
Yes, this is a truly remarkable piece of experimental physics published in Nature Physics by an international team, prominently including Ian Moss and Tom Billum from Newcastle University. Now, to be perfectly clear, they did not trigger a cosmic Higgs decay. Doing so would have destroyed the Earth and the universe. Instead, they created a highly sophisticated quantum analog system.
Break that down for me. How do you put the apocalypse of the universe into a petri dish?
They utilized a state of matter called a Bose-Einstein condensate. They took a cloud of sodium atoms and cooled it down using lasers and magnetic traps to less than a microkelvin above absolute zero. That is incredibly cold, colder than the deepest depths of intergalactic space. At these ultra-cold temperatures, the individual atoms lose their discrete identities. They blur together, and the entire gas behaves as a single macroscopic quantum entity, a ferromagnetic superfluid.
Okay, so you have a super cold, fluid-like cloud of magnetic atoms. How does that simulate the universe?
By carefully manipulating external radio frequency and magnetic fields, the researchers were able to create a double minimum energy landscape for the spin states of the sodium atoms. They engineered an energy map that perfectly mathematically mimics the exact shape of the Higgs potential. They created a false vacuum local minimum, an energy barrier, and a deeper true vacuum minimum. Then, they carefully prepared the entire cloud of atoms so they were resting entirely in the higher energy local minimum, the false vacuum.
They built the gutter and they stuck the marble in it.
Exactly. And then they simply watched. They maintained the system and observed it, and what they saw was macroscopic quantum tunneling. Small, localized regions of the superchilled gas spontaneously transitioned through the energy barrier to the lower energy true vacuum state. They actually saw bubbles of true vacuum nucleate and begin to expand through the atomic cloud.
They saw the bubbles, the literal physical manifestation of Sidney Coleman's math.
They did. Furthermore, they observed that the transition in their system was primarily thermally activated, driven by microscopic thermal fluctuations in the gas. They directly measured how the core energy gained by the bubble dropping to the true vacuum perfectly compensated for the positive kinetic energy cost of the domain wall, the bubble's surface tension. The atomic fluid behaved precisely as Coleman's equations predicted the fabric of space-time would in a cosmological setting.
My mind is completely blown. We built a microscopic scale model of reality deleting itself just to see if the terrifying math on the chalkboard actually translated into physical reality. And it worked. Even if it is just an atomic analog, it proves the math isn't just theoretical fantasy. Bubble nucleation is a real observable physical process. The math is real. The trapdoor is real.
It confirms the complex dynamics of quantum field theory in non-equilibrium states. It gives physicists a tangible, controllable platform in a laboratory to study how these bubbles form, how fast they grow, and exactly how thermal fluctuations and impurities affect the tunneling rate. It is a massive, historic step forward in understanding the deep mechanics of metastability.
Okay. I am officially profoundly terrified. Reality is a house of cards, the math works, the trapdoor is real, and we just proved it in a lab with cold sodium. I desperately need some good news here. Confronted with this overwhelming existential dread, is there any comfort whatsoever to be found in the physics?
There are two main avenues of comfort, though they depend heavily on your philosophical perspective of the universe. The first comfort comes from the macro-scale field of cosmology, specifically regarding the accelerating expansion of the universe.
Dark energy. The thing pulling galaxies apart.
Yes. The universe is not static, it is expanding. And since the late 1990s, we've known that this expansion is accelerating due to dark energy. Because of this, the actual fabric of space itself is stretching. Now, if you look at galaxies that are sufficiently incredibly far away from us, roughly 14 billion light-years away, the cumulative stretching of space between us and them is so massive that they appear to be receding from us at a speed faster than the speed of light.
Wait, let me stop you right there. I thought absolutely nothing could move faster than the speed of light. Isn't that Einstein's golden rule?
Nothing can move through space faster than light. That rule holds true. But general relativity allows for space itself to expand at any arbitrary speed. Space is the canvas. The canvas can stretch faster than the paint can move. This incredible expansion creates a hard mathematical boundary known as a cosmic event horizon. Any light, any gravitational wave, or any signal of any kind emitted from beyond that horizon can never ever reach us. Why? Because the space between us and the incoming signal is literally expanding faster than the signal can travel through it.
Okay, I think I see where you're going with this. How does this help us with the vacuum decay bubble?
Remember our discussion on causality. The vacuum decay bubble wall expands at exactly or imperceptibly close to the speed of light. It absolutely obeys the laws of relativity and causality. Therefore, a vacuum decay bubble is strictly limited by the cosmic event horizon. Meaning, if a bubble of true vacuum randomly nucleates in a galaxy 15 billion light years away, it will expand outward forever, destroying everything it touches. But because that galaxy is beyond our cosmic horizon, the space between us and the expanding bubble wall is expanding faster than the wall can travel. The bubble can never mathematically ever reach Earth.
Oh, wow. So the universe essentially has built-in quarantine zones.
That is a highly accurate, very evocative way to conceptualize it. The universe is completely causally compartmentalized. Because of dark energy, vacuum decay cannot destroy the entire infinite universe. It can only destroy the causally connected accessible region of space where it originally started. If a bubble starts next door in the Andromeda Galaxy, yes, we are toast. The light speed wall will eventually hit us. But if it starts across the cosmic horizon, we would never even know it happened, and we would remain perfectly safe for eternity.
I actually find a bizarre, profound solace in that. It's like looking at a map of a global forest fire, but realizing there are infinite, uncrossable fire breaks permanently built into the very fabric of the Earth.
It ensures that even if vacuum decay is happening constantly, all the time, across the infinite, unending expanse of the greater universe, there will always be pockets of false vacuum. There will always be isolated islands of life, chemistry, and structure that remain entirely untouched by the decay.
That is incredibly comforting. What is the second avenue of comfort?
The second is a deeply speculative, highly mathematical, but incredibly beautiful theoretical framework regarding cyclical cosmology. The physicist Matt W. discusses this heavily in his writings, attempting to connect the metastability of the Higgs field to broader theories like the Big Bounce or Sir Roger Penrose's conformal cyclical cosmology known as CCC.
The idea that the universe doesn't just have one beginning and one end, but goes through endless cycles of death and rebirth.
Exactly. Let's look at the current trajectory of our universe. We currently face the very grim prospect of a cosmic heat death. Trillions upon trillions of years from now, all the usable gas will be exhausted. The last stars will burn out and go dark. Galaxies will drift unimaginably far apart. Even the supermassive black holes will eventually evaporate into Hawking radiation. The universe will become a cold, dark, infinitely expanding, empty void. It is a slow, agonizing, rather bleak end.
Very bleak. The ultimate fading into nothingness.
But what if false vacuum decay is not a catastrophic bug in the system, but a necessary engineered feature? In these cyclical cosmological models, the Higgs metastability provides a physical mechanism for a cosmic reset. Imagine that dead, freezing, infinitely expanded, empty universe. Suddenly, purely by quantum chance, a vacuum decay event triggers. A bubble of true vacuum nucleates. It sweeps through the dead void at the speed of light. It drastically resets the laws of physics. It radically alters the fundamental constants.
And in doing so, it releases all that pent-up massive vacuum energy stored in the false vacuum.
Yes, an incomprehensible amount of energy is released. In some highly speculative mathematical models, this violent transition, this sudden, aggressive restructuring of space-time and release of vacuum energy, could act as the exact catalyst required for a new Big Bang. The violent death of our current universe via vacuum decay literally sows the energetic seeds for the high-energy, fiery beginning of a brand new universe.
So maybe, in the absolute deepest, darkest future, when all the stars are gone and time has practically lost its meaning, this terrifying decay is exactly what the universe desperately needs to be born again. It is the ultimate cosmic recycling program, the phoenix burning itself to ash to be reborn.
It remains highly speculative, of course. The mathematics of transitioning matter and information through a singularity or a quantum bounce and retaining a viable structured universe on the other side requires incredibly complex, currently unproven physics linking general relativity and quantum mechanics. But it is an undeniably elegant concept. It frames the metastability of the Higgs field not as a cruel sword of Damocles dangling over our heads, but as the steady, inevitable heartbeat of an eternal cyclical cosmos.
It changes it from an executioner into a midwife.
Precisely.
Synthesis time. We have covered an immense amount of ground today. We completely shattered the illusion of empty space, realizing we live in a thick ocean of Higgs energy. We looked at the terrifying math of the cosmic valley and how weighing the top quark revealed the trapdoor beneath reality. We explored the quantum triggers of bubble nucleation, the fact that this bubble expands at the speed of light, ensuring we would never see it coming, and the horror of the big crunch waiting inside. We looked at whether alien technology could press the button. We saw a macroscopic scale model of the apocalypse happen in a petri dish full of cold sodium. And finally, we found a glimmer of hope in cosmic quarantine zones and the rebirth of the universe.
It is a profound testament to the brutal, unyielding, yet beautiful elegance of the Standard Model. It is truly remarkable how far scientific understanding has come. By simply building a machine to collide protons together and meticulously measuring the scattered subatomic debris, human beings have deduced the exact mass of the Higgs boson and the top quark. And from those two incredibly tiny numbers, we can trace a direct, unbroken mathematical line to the structural integrity of reality itself. We can predict the ultimate vulnerability of the vacuum we inhabit. Whether we are perfectly stable or precariously metastable, the mathematics describe a universe that is profoundly, deeply interconnected, from the smallest invisible subatomic quantum fluctuation to the macroscopic final fate of spacetime.
The universe has a secret trapdoor. And with nothing but math and curiosity, we've managed to draw a map of exactly where it might be. So what does this all mean for you, the listener? How do you go about your day knowing this? Well, the next time you step outside on a clear night and look up at the seemingly empty, peaceful, dark sky between the stars, I want you to remember, it isn't empty. The darkness is an ocean, filled to the absolute brim with a heavy, invisible energy. And right now, as you take your next breath, that ocean is precariously balanced on a microscopic quantum ledge, holding the shape of our reality, our chemistry, and our lives together by the slimmest of mathematical margins. It is stable enough to give us a beautiful universe to live in, but fragile enough that it might not last forever. Sleep tight,